Hello, my name is Shunta Muto, and I attend Tufts University. I'm a mechanical engineering major. Before we go into lunch, let's talk about nitrous oxide, specifically on investigating nitrous oxide sources of agricultural emission. So what is nitrous oxide? Nitrous oxide is a greenhouse gas that mainly comes from agricultural soils. And it is 298 times stronger than CO2. And even though EPA estimates that only 5% of greenhouse gas comes from nitrous oxide, it has great uncertainty in the estimate because of a lot of the complex biological processes that takes within the soils. It's also important because it's increasing every year, and the lifetime is 110 years. It probably lives longer than me. And in 2012, it was shown that it is now the largest ozone depletion compound that is emitted from the human activities. Yet there's no strict regulation that is placed on the emission. So how do people estimate the N2O? Well, California Air Resources Board is required to report the values every year. And what they do is they go through this bottom-up approach in which they list all the processes that are involved in the N2O production process, estimate the emission for each of them, and then summing them up to come up with the total emission in the entire California. So let's look at the manure management section. If you look there, you can see the equation that they use. I have no clue what these variables are, but the big takeaway from this equation is that it depends on many things that are spatially and temporally variable. If you look at another example, fertilizer emission is dependent on the crop types and soil properties, which if you look at the map on San Joaquin Valley, we know that it is vastly spatially different, spatially variable. So what I want in order to apportion the sources of N2O is not this table that just lists out the total values, but rather a picture like that shows the spatial distribution, that shows the spatial distribution of emission. However, we know that this picture is from in-situ measurement from the aircraft. So in-situ measurement, you can't really fly everywhere to take measurements anywhere. And it is also hard to infer the sources just by measuring the concentration of the N2O. So majority of my method consists of making high resolution emission map that is based on the inventories and comparing that with the in-situ measurement. And I'll be focusing on these three counties where we flew over. It is the southern San Joaquin Valley. So in order to start off with my making high resolution map, I started off by dividing the map into smaller grids. And I defined that grids to be 5 by 5 kilometers, considering that I'll need to compare this with the in-situ measurement later. So this should give me enough points from the in-situ measurement to compare later. If you zoom into one of these grids, you can see that each grid contains different types of land. So dairies is where the dairy cattle reside, and feedlots is where all the other cattle reside, is what I assumed. And what I want to do here is to calculate the emission or estimate the emission coming from each of these categorized land and sum them up to get the emission coming from one grid or coming from each grid. So in order to do that, I use the carbs inventory heavily. And if you look at the carbs inventory, you can see that each of the processes are categorized depending or according to how the emission takes place. But if you look closely enough, you could assume that it could be recategorized according to where the emission takes place. So for example, all the ones that are shown by yellow could be attributed to the land that is categorized as dairies. So after recategorizing, I came up with this table, which has now 5 categories. And once you recategorize by the land type, you can now attribute the sources spatially. So in order to quantify the emission from each of these categorized land, I again use carbs inventory and also other statistics or US census stats. So from the carbs inventory, I can get the N2O or CH4 emission that would come from one dairy cattle, from each dairy cattle. And using the population data from US Census, I can get the population of dairy in my region of interest. And using the ArcGIS or GIS data, I can also get the total acres of dairy in my region of interest. Combining all that, I can come up with the emission, annual emission per year that is coming from 1 acre of dairy in my region of interest. So for fertilized land, it's a little bit different because the different amount of fertilizer is applied for different croplands. But as long as we know what kind of croplands that we have in each grid, which we know from the GIS data, we can multiply by that by the N2O production rate of fertilizer, which is given by the carbs inventory, to come up with how much emission is coming from fertilizer in this grid. So at the end, I can sum all this up to come up with the total emission that is coming from this, from each of the grid. And if I do this for the entire southern San Joaquin Valley, I should be able to come up with the spatial distribution of emission of N2O or CH4. I'll talk about CH4 later, for the entire southern San Joaquin Valley. So I said earlier that I needed to compare with the in-situ measurement later. So here is one snippet of the in-situ measurement. But what I did for this is to take average of all the points collected in each grid. So here's the result. On the right, you can see the in-situ measurement. On the left is the high-resolution estimate that from my estimate. And you can see that the general trend agrees. For example, south of Hanford, you can see a hotspot there. But what's happening in Bakersfield? There's a hotspot seen in the in-situ measurement, but not my estimate. So I wanted to know what this region is about. So if you look at this region on the map, you can see that there's a lot of industrial facilities, which was very striking because I said earlier that N2O comes from agricultural source and not the industrial source. So there's a lot of explanation that can be said for this, but one speculation I have right now is that because this region is close to the edge of the valley, it is where the air kind of gets stagnates, causing the accumulation of N2O. So let's look at, so another thing I did is to use a high resolution map method, just as the same method to the methane, and looking at the ratio between N2O and CH4. And because they both come from agricultural source, I can see the correlation between them and look at the slope to see if I can infer the fingerprints that is coming from agricultural emission. So I did this for both my estimate and the carbs for the in-situ measurement as well, and compared. And you can see that I miss a hotspot again, this time twice. But if you look at this circle right here, you can see that this region is region with a lot of cotton fields. And from the surveys conducted from the farmers, I learned that fertilizer is applied mostly at some point during May through July, which is right during our SARP campaign. So this means that it's likely that fertilizer was applied near our flight days. So this could be a total coincidence, but it's really important to investigate this because we might possibly be able to explain why there's such a seasonal and temporal variation in the emission of N2O in San Joaquin Valley. And there's a study done by Zhang that shows that there's much more emission during summer than annual emission rate estimated by other inventories. And the previous result that I showed could explain why this is true, because I just showed that the time of application of fertilizer could drastically affect the emission rate in that region. So as a conclusion, I was able to recategorize by the land type and compare that with the in-situ measurement, and I got into a general agreement. But there's a lot of hotspots that I missed due to the temporal variation. So in-situ measurement must always has to be used with this bottom-up approach in order to account for that gap. And also, I raised a question about the bottom-up methodology of CARB and other inventories. And so when you think about the mitigation strategies for these emissions of N2O or CH4, you need to think about that, you need to consider about the temporal and spatial variation and how much that affects. So my next step is, if I have time, would be to investigate that industrial facilities region. Where is that N2O coming from? And also, I never was able to quantify the actual fingerprints of the N2O and CH4 ratio. So I would love to do that if I have time. Lastly, I'd like to acknowledge Dr. Sally City, my mentor Soli, thank you, and everyone in my TikTok group and everyone in this room.